Assalamu alaikum. So we are discussing different characteristics of mechanism, and in our last lecture we have done one of the problem related to reciprocating mechanism, and a method was discussed to draw the schematic of reciprocating mechanism, mainly for the slider crank linkage, and we were given advance to return ratio and as well as the stroke. So you have to work out the other lengths of other linkages. So this was one of the example for reciprocating mechanism, and before that we have done some other mechanism like swinging or rocking, indexing mechanism, so on. So there are many different characteristics of mechanism which are being in discussion until now. And after reciprocating mechanism, along with solving a problem, the other category, the famous category, is reversing mechanism. So when a mechanism capable of delivering output rotation in either direction is desired, some of reversing mechanism is required. So basically the reversing mechanism is able to do work in both direction. So it's a forward and reverse in both direction. Many such devices make use of two-way clutch that connects the output shaft to either of two drive shafts turning in opposite direction. This method is used in both gears and belt drives and does not require that the drive be stopped to change the direction. So there are many different possible variations, and in this combination it is also not necessary that we need to stop it to do the reverse function. So gear shift devices, as in automotive transmission, are also in common use. So the mechanism which is used for gear shift, for example, a particular of interest is when you are doing forward and reverse gear shift. So in such scenario, these reversing mechanisms are basically being used. All right, so the next category is coupling and connectors. So coupling and connectors are used to transmit motion between coaxial, parallel, intersecting, or locked shaft. So basically, couplings or the connectors are the one which are used to transmit motion energy from drive to driven, basically. So now those combinations could be part of could be parallel, coaxial, intersecting, or skewed. So gears of one kind or another can be used for any of these situations. So these will be in chapter 7 and 8, and of course we will also study some of these applications when we talk about gears. Flat belts can be used to transmit motion between parallel shafts. They can also be used between intersecting or skewed shaft if guide pulley are used. So this is one of the example, which is basically intersecting shafts. So what does it mean? So you got one shaft here, and this is another shaft. So they are kind of like intersecting. So that's why they're being termed as intersecting. But we certainly need some guiding pulley in between those, as shown in figure. When parallel shafts are involved, the belts can be open or crossed depending on the direction of rotation desired. So it really depends on the direction. So you can have the open belt or cross belt as well. This is a further classification for coupling. So the relux coupling shown in figure 1.1a. So this is one of the couplings. So you see This is one of the shaft rotating this way. This is another shaft rotating this way. So of course this coupling then makes like rotation along this axis as well. So this is another example for intersecting. You see, this is one of the shaft going through this one, and this is another shaft. So they are intersecting at some certain point. So that's why they are called as the intersecting shaft. The other very famous example is a hook joint, basically. So we will also study hook joint. So you see, this is also a possibility of intersecting shafts. So this is one shaft, the other shaft. The axes are intersecting at this particular point, but it has an additional flexibility. So for example, this shaft can rotate, can move up and down as well. So, however, this joint can withstand heavy loads and is commonly used with a drive shaft in a rail wheel drive vehicles. I'm quite sure you have seen such hook joints where the rear wheel drive applications. So the engine is at the front and the drive, so the wheels are driven at the rear, and the connection between them is done through a shaft. And because the wheels has to move up and down in a vehicle. So for example, if you have the engine over here and you want to deliver power to the rear wheel, so there is a shaft. So shaft needs to be flexible so that if this move up and down, because this is the way the vehicles work, the suspension. So in that case, the shaft should not break. So to avoid that, one of these hook joint is used. And if you see in a heavy duty trucks and rear wheel drive vehicles, you will see below such combination where the such shafts or joints are used. So it's customary to use two of these joints in series for connecting parallel shafts. It really depends on the number of combinations, so that can be employed. The next category is about pause and hesitation mechanism. So this is one of the general classification, which is again being discussed in the same paper, which is being mentioned here, Professor. So all these are being classified in one big category. So in an automotive engine, a valve must open, remain open for a short period of time, and then close. So you see, a valve in automotive engine has to do series of different works. So it has to be open and then remain open for short some period of time, and then it closes. A conveyor line may need to halt for interval of time while an operation is being performed, and then continue its motion. So this is another example where intermittent or stop play work has to be required, basically. So this conveyor line has to stop for some time and then has to move again. Many similar requirements occur in the design of a machine. So Professor classifies these as, so he has done this classification like stop and dwell, stop and run, stop and advance, and so on. Such requirements can often be met using cam and follower mechanism, indexing mechanism, including those in figure, ratchets, linkage at the limits of their motion, and gear and clutch mechanisms. So there are many different applications. Cam and follower is one of the very good example, and indexing mechanism, which we have studied already, they are also in the same category. Ratchets, linkages, and the limits of their motion. So there are versatile applications. So that's why this category is also huge as well. So the 6-bar linkage, as shown in this figure 1.22, is a clever method to obtain a rocking mechanism. So basically, we required a rocking mechanism at this particular point C, uh, which with the connection with the link 6. So you see when it is moving, so if it's moving up and down, link 6 doing the rock mechanism. mechanism like rocking movement. And extend the coupler. So this whole element, this is a coupler and a rocker. So rocker 4. So this is the rocker. So this is also moving in this direction, being termed as rocker. Can be designed such that point C on the coupler generates the curve shown by dashed line. So this curve you see is moving up and down kind of movement. A portion of this curve will then fit closely to a circular arc whose radius is equal to the length of link 5. That is the distance DC. So this distance, this DC, this distance. When point C traverses this portion of the coupler curves, link 6, the output rocker is stationary. So even though we do the movement, but this link 6 could be stationary as well. So this is quite one of very interesting example where such combinations of links are joined in such a way. So some links could be stationary, but we still are able to get the rocking motion basically. Yeah. So in continuation of these one, in the same chapter from the theory of machine and mechanism, there are further examples including curve generators, for example. So this stop, pause and hesitation mechanism could also be part of curve generator where curve generation is required. If you're interested in, you can just visit the same chapter 1 of theory of machine and mechanism by Shigley and read it by yourself basically. So these are also basically required to generate curves or even the straight line generators. So next top discussion is kinematic inversion. So kinematic inversion is an interesting topic. So what is so in section 1.4 we noted that every mechanism has a fixed link called the frame. So in any mechanism, the one which has fixed link normally being in many different mechanisms we have seen. So wherever you change different frame within that mechanism. So when I say change frame, what does it mean? You fix the link to behave as if, so let's say you have a 4-bar mechanism. So you have 4 bars, 4 links. So one by one, you fix one link. When I say fix, means you restrain this movement. You fix one link and other links will keep moving. So the relative motion between various links will not be different actually. So because you are just moving one of the link and you are keeping one of the link fixed, and then other links has to move relative to the fixed link in certain way. So that's why the relative motion will not change. But their absolute motion, those measured with respect to frame, may be changed. The relative motion is not changing, but their absolute motion is changing. We will have one example in next pages. We will see. You will have better understanding. So the absolute motion may change significantly. So you see, you have quite a lot of variation. The process of choosing different links for the frame is known as kinematic inversion. So the process itself is called as a kinematic inversion, where you just choose one by one different frames. For example, in an n-link mechanism, choosing each link in turn as the frame yields n distinct kinematic inversions, that is n different mechanisms. So there are different ways you can look at it. If there are n mechanism in one of the category, so let me give you one example. For example, you got one mechanism. So for example, this is one of the mechanism. So you got link 1, this is link 2, this is link 3, this is link 4, this is link 5, right? Ignore this bit, ignore it. So let's say you keep this one as a frame, so other will perform some function, so they have some mobility. In the next step, you keep this as a frame, you keep this one as a fix, and all other can move. In the next phase, you keep this one fixed and all other can move. So keep going on. So let's see, there are n is equal to 5. So there are 5 links. So there are 5 different variations, and such is called as a kinematic inversion. So this mechanism has 5 different kinematic inversions basically. So you see the relative motion between links is still same. For example, this has to move this direction, this has to move this direction with respect to this, but absolute functionality would be different. So the movement would be different in such combination. This is one of the example. For example, consider a slider crank linkage. So this is one of the slider crank linkage. This is figure 1.27a, shows the first inversion. So this is very first type of the inversion for 4-bar linkage, which is found in most internal combustion engine. So this inversion basically, this particular type is very common in internal combustion engine, where the frame is this cylinder block. So this cylinder block is a frame. One is a frame, so it's not moving. Yeah. This is very common example for internal combustion engine. And link 4. So this link 4 is the piston is driven by expanding gases, and this movement provides the input. So you see when you have the expanding gases, so this will provide the movement. Link 3, the connecting rod. So this link 3 is a connecting rod. Connects link 2, this one, the crank. So you see the crank is supposed to moving like that, which rotates as driven output. So by reversing the role of input and output, the linkage can be used as a compressor. So you know that the difference between compressor and engine. So in typical engine, you have the high pressure gases which moves the piston and which pushes this connecting rod, and that connecting rod helps to move the crankshaft in one of the categories. So you take useful energy from this point A. Second category, where you just change driver and driven. So you put the motor over here. So you still have the crank, you have the connecting rod, you have the piston. But now this time, because you are moving this crankshaft, so you are basically giving energy to the gases. And that is what we call as a compressor, basically reciprocating compressor. So in this case, this particular example, this is one of the kinematic inversion, which is 4-bar link, the very famous internal combustion engine. So we will now discuss the different inversions here. So we will keep different combinations actually. So the next category is, this is 1.27b, shows another kinematic inversion where link 2 is stationary. So this time link 2 is being held as a stationary. So you got this particular point, This one with reference to this one is also stationary. So link 1, formally the frame, now rotates about revolute A. So you got this particular point. So this one link can move up and down. So it can rotate potentially. This inversion of slider crank linkage was the basis of rotary engine found in many early aircraft. So I'm quite sure in thermodynamics module in your early years you would have studied about rotary engine. So this is one of the example. So this can move up and down this whole cylinder, and yeah, so such combination will be called as a kinematic inversion, another kinematic inversion. And it is basically a 4-bar link because we still got 4 links operating, but now instead of cylinder, one of this link 2, which was basically crank over there, now it's been stationary. So this is a frame basically. So this is another example. This is the third kinematic inversion. So yet another is shown in figure 1.727c. It has link 3, formerly the connecting rod. So link 3, this one, as the fixed link. So this is one of the fixed link now basically. So this linkage was used to drive the wheels of early steam locomotive. So locomotive application used to have such combination, with link 2 being attached to the wheel. So link 2, this is being attached to the wheel, and this is the stationary part. Connecting rod is a stationary. So now you can just think about it, how this motion could happen. So this kind of like oscillates in this direction, and because this link is fixed, is fixed with respect to link 4, so this can oscillate to and fro basically. So this is another inversion. So in continuation of that, the last one is the final inversion shown in figure 1.27d. This D has the piston, got the piston link 4, which is stationary. So you see the link piston itself is stationary, although it is not found in engines. By rotating the figure 90-degree clockwise, so for example you keep this one as over here, the linkage is recognized as part of garden water pump basically. So this is, for example, the link 1 moving up and down. So this is one of the example for garden pump. Note this inversion, that the prismatic joint connecting link 1 and 4. So link 1 and 4 is because it's moving up and down. So this is one of the prismatic joint. When we were studying the lower pairs, so this such category is called the prismatic joint is inverted. That is, the inside and outside element of the joints are reversed. So this is basically one of the categories. So where link 1 is moving up and down. So it's been reversed from the prismatic joint, which was studied in the same lecture uh, in the category of lower pairs. The next topic is about the application of Grosh of Law. This is one of very famous law which is being used for mechanics mechanisms. So uh, what it says, a very important consideration when designing a mechanism is to be driven by a motor, obviously, is to ensure the input crank can make a complete revolution. So in the example, what he's saying, the important consideration, the mechanism is connected with the motor. So if it's connected with the motor, then one of the link which is connected with motor has to do complete revolution. So complete circle movement has to be done by, if it's a connecting with the motor. And why we are connecting with the motor? Because any useful work we want to get from a mechanism is by connecting it with the motor. So is to ensure the input crank. So one of the link which connects to the motor and rotates, that basically would be called as a crank, as we have been discussing. It has to make complete revolution. So mechanism in which no link can make a complete revolution would not be useful in such application. For example, you have one mechanism in which the crank is unable to do complete revolution. Such combinations would not be of useful because we cannot connect to the motor. So if you're not able to connect to the motor, so basically the mechanism itself is not really useful then. Yeah. So for the 4-bar linkage, there is a very simple test whether this is the case. So now Grosh of Law, which is very simple way to evaluate in a very simple words. So Grosh of Law helps you to find out if the link will make complete revolution or no. That's it. So what it says, and this is for 4-bar linkage particularly. So Grosh of Law states that for a planar 4-bar linkage, the sum of a shortest and longest link lengths. So if you have a 4-bar linkage, you got a 4-bar linkage, and among those 4-bar, what it says, the sum of the shortest and longest. For example, this is sum of shortest and this is the longest links length cannot be greater than the sum of remaining two links. So you sum these two, the other two basically the middle one. So one is the shortest, one is the longest, and the other two remaining, if there is to be continuous relative motion between two links, so the sum of shortest and longest links lengths cannot be greater than the sum of remaining two. So small and lengthy link, if you add together, they must not be greater than sum of other two. So this is another explanation. So this is shown in figure 1.828, which is the next page, where the longest link has length L. So the length L is basically the longest link. The shortest link has length S. The shortest is S. And the other two links have lengths P and Q. So other two links doesn't matter because they are in middle. So the shortest S and the longest is L. And in between these two, you have P and Q. So in this notation, Grosh's law states that one of the links in perpendicular to the shortest link will rotate continuously relative to other three links if and only if. So this will rotate complete revolution only if shortest and longest link, the sum of both is less than equal to, you see, less than equal to the sum of other two links. I'm quite sure when we do some problem, you will see how is it easy actually to implement such thing. So let us say if this inequality is not satisfied, no link will make a complete revolution. So none of the link will make a complete revolution if this inequality, if this condition is not fulfilled. So this is a very simple test basically. Once again, why we need this test? Because we want to see if the crank will rotate complete, will have a complete revolution. And why we need to check this? Because if it doesn't make complete revolution, if it's connected with the motor to perform a useful work, for example in a compressor, so it will not be able to rotate complete, means you cannot do any useful work from the from the setup basically. Yeah. So this approach, the problem somewhat differently, but of course obtains the same results. In this approach, for using figure 1.29, so this is the figure 1.29, which is a combination of different figures. So the links are labeled. So S is termed as the crank, which is the shortest link. L is a coupler, which is the longest basically. P is the lever and Q is the frame. So in this combination, so some such things are discussed. So S is basically crank, L is a coupler, P and Q are basically, so Q is the frame, yeah. So Q is the frame, and P is the basically lever. So where L needs not to be longest link, then the following condition is applied. All right, yeah. So basically, 4 different combinations are given. So what you do, so you have this example, you can bring one of the P or Q on this side. So that's what it says. So you bring P on one side. So that's why you got S plus L plus P greater than Q, S plus L minus P less than Q, S plus P plus Q greater than L, S plus Q. So these are different possible variations of this equation. So if you read it carefully, all these 4 equations are basically variation of this equation. So you can write this in 4 different ways. If these 4 conditions are not satisfied, then the results are as illustrated in figure 1.29. So if these are the conditions, they are not satisfied, as I said. So these are basically 4 different conditions which are taken from this major equation. If they are not fulfilled, so what would happen then? So one of the example, 1.7a. So this is 1.7a. So this is the equation. S plus L plus P is less than Q. So you see, Q is the frame which is longest here. So if you sum S plus L plus P, and it is still less than Q. Q is a frame, and the links cannot be connected. So if this equation is there, in that case, so you see, this was so for example, how this visually be explained. This is explained in such a way where Q is larger than some of these 3 links. So means we are unable to connect those 3. So they are there. You cannot connect it because the length Q is much larger than the sum of all these 3. So of course you cannot do any useful work from it because it's not connected. This combination is not being connected. In the second example, which is 1.7b, so S plus L minus P greater than Q. Yeah. So again, I will show you this example. So S plus L minus P less than Q. So this was the condition. But now what we are saying, if this combination S plus L minus P greater than Q, so it will also not work. What is it basically? Now you see. So this is the S crank, this is L coupler, and this is P. You subtract it, so that's why you have like it's going on the other end, and this is P. So now what happens is an incapable of rotation. So you just imagine visually, this S cannot make any revolution. Why? Because this coupler length is so long, so it will not allow to move complete revolutions basically. So if it's, you just imagine yourself, with this combination, if you want to rotate this one, so what will happen, this link will rotate downward, this L, and now this might go up and down. So it is quite ambiguous situation. So that's why you cannot get a good rotation from here as well. This is another example. So in the next category, C, which was this equation 1.7C, so S plus Q plus P greater than L. Now it's been written like that, S plus P, Q plus P less than L. So if this is the case, so we have the Q, so S plus L plus P, they are all, the combination of all three is less than L, and the links cannot be connected. So you see the links in this combination, we are unable to connect those because the lengths S, L, P are so big than the frame, so you cannot connect those. So of course, when you are not able to connect it, so these are not connected. So if you are unable to connect, so means you cannot do any useful work from here then. Next category, D. So D equation is S plus Q minus P less than L. So what it says, so if you write another way around, S plus PQ minus P, if it's greater than L, so you do S plus L minus P, and it is greater than, sorry, S plus Q minus P is greater than L. So you see this combination will be there, and if you try to move it, you cannot move it because it has to reach at this point because you know, in a normal operation, this point should be here when this one is over here. So if they are not in one line, what does it mean? So you want to move this one here, but it cannot move because the length is short. So that's why this is another combination which is not capable of having any rotation. So you see, this Grosh of Law is very useful, and which is quite valid for and easy to understand for 4-bar links. And you can write down these combination, or at least you can work out these one, which is very simple. So shortest and longest must be less than equal to P plus Q, or sum of other two links. So if you perform this test on a 4-bar link, you can easily say that will it work or no. That's the answer you will get from Grosh of Law. Will it work means the crank is able to rotate with a complete revolution. If it's not able to rotate, means you are not getting any useful work from it. So this is next, we have one of the example. Yeah, so we can do this example. So what it says, this is example 1.6. So is the linkage shown in figure 1.30? This is 1.30. A crank rocker, a double rocker, or a drag link 4-bar. So we need to decide what category of this link is basically this mechanism is. We have been given different lengths. We got a P. P is one of this one. This is 4 inch. L, which is the longest, which is 6 inch. Q, I think this is missing, so it would be given. And S is 3 inch, so this is 3 inch given. So we need to check basically. So yeah, so one of these one is basically missing. 4, 6, and 4, 6. This must be 5. So this is 5. Yeah. So this is 5. So substituting in the equation 1.6. So 3 plus 6 shortest. longest, shortest is 3 inches, longest is 6 inch, 3 plus 6, 9, and the sum of other two, which is 4 plus 5. So you see 9 inch less than equal to 9. So this condition is fulfilled. So therefore the linkage satisfied Grosh of law, that is the linkage is Grosh of 4-bar linkage. So this will be called as a Grosh of, because it's fulfilling the condition, that's why it's being named 4-bar linkage. Since the shortest link is the frame, the two links adjacent to the shorter link can both rotate continuously. So because if let's say it was a conventional 4-bar linkage, this has to rotate, but now this S is a stationary, so it's not moving in this combination. So that's why the adjacent to these ones, so this will make complete rotation and this will make complete rotation continuously. So you keep moving one and the other will keep moving. And both are properly described as a cranks. You can call them as a crank both because both are moving. Therefore, figure 1.3 shows a drag link linkage. So this is one of the drag link linkage because both are moving continuously. This is one of the definitions for drag link 4-bar linkage. So that's why we can call it as such. So you see, this Grosh of law is very interesting law basically. Why it is very interesting? Because you are in a phase of designing a mechanism. So you know the lengths and everything, and you want to get some useful work. But before manufacturing mechanism, you just check through this equation. You check through this equation, and you will see if your link will be doing any useful work or no. If it's satisfying, for sure it will do the work. If it's not satisfied, means you are unable to do any useful work with this one. So that's one of the category or one of the rule we can check basically. Yeah.